Welcome to Unit 2, Trigonometric and Periodic Functions. This unit will tackle the trigonometric functions as well as periodic functions, or the so-called sinusoidal functions, or those functions that oscillate like a wave. For example, the sine function, the cosine function, the tangent function, and the inverses of these functions. So we will begin this unit with chapter 5, and chapter 5 is about periodic functions and right triangle problems. So as you can see here, a picture of ice skater Michelle Kwan rotates through 90 degrees during her spin. So of course in ballet or in snow ballets like that, especially in ice skating, okay, the contestants and the performers normally rotate through many positions, and normally they are in angular degrees. So look at her hands. They extend and then they come back to the same position at each of the rotation. So this is actually giving us a periodic function, okay, because it goes from one point to another and then comes back to the origin, to where it come from. So the hand, as it rotates, for example, it came from 180 degrees from your left. Okay, so from your left, look at your left hand, and then measure 180 degrees to your right hand. So now you have the extended hands, and you have 180 degrees. If, for example, you rotate to about another 180 degrees, you will land up to the same position. Am I correct? So that is what we mean by periodic functions. Okay, but you know, periodic functions is not only about having 180 degrees, okay? Because we will discuss it later, how, you know, these periods and periodic functions are in a way related to each other. So let us go to lesson 5-1. Lesson 5-1 is an introduction to the periodic functions. So our objective for this lesson is to find a function that corresponds to the graph in figure 2-1b and graph it on your grapher. So figure 2-1b is this. I forgot to label it with a figure 2-1b. Okay, so what do you see in this figure? You see a rotating Ferris wheel. Okay, this is a Ferris wheel, and these Ferris wheel are important, especially in occasions like circuses and what else? There's normally we see them in carnivals, carnival parts. Okay, so as you could see, if the Ferris wheel is run, the wheel itself rotates from, let's say this is the point of rotation. Okay, this is, for example, the point of rotation is, the center is here. Okay, and let's say it started rotating from here. Now this Ferris wheel will rotate into a circular motion, going through any angles within this circle up to where it came from. So from here, from this point, it rotates to an increasing height until it reaches a maximum height, which is directly opposite from beginning. Okay, and then it comes down, going back to the same position. Now that one rotation or going back to the same position is what we call a period. So it's one period. So if you go from A and then you travel again to A, that is one period. Okay? But this Ferris wheel does not stop there. It continues going on and going on and going on, rotating and rotating until it stops for a certain period of time until the first what do you call this, the first series of rotations is done, right? So this is usually including, when you pay for a Ferris wheel ride, you get to ride for maybe a minute, right? Or at least 30 seconds or a minute. So that's the time of rotation of the Ferris wheel that you rode in. Now remember, for that minute where you rode the Ferris wheel, how many degrees of rotation did it actually accomplish? So you could say that maybe you've gone to 10 periods or 10 rotations, which is equivalent to 10 periods, right? And still you will land up on the same position, this position. Okay, so in the periodic functions, especially in sine and cosine, this period or this position has its own term. So let's keep going. Now we have this Ferris wheel. And this Ferris wheel, okay, now as you ride through that Ferris wheel, your distance from the ground depends on the number of degrees the wheel has rotated. Am I correct? So this is actually illustrated by this scenario here, these graphics. So as you move away from the position, let's say you came from here, okay, and then you went up, or maybe you came from here, okay, and there is a certain height from there already, and that height is, let's say, 11 meters. Okay, now as you go through the wheel ride, notice that it rotates to certain angles. So your distance from the ground also changes, right? So when you go up, your height or the position from the ground to a certain level in the Ferris wheel is also changed into a certain height. Okay, and now that height with the angle theta, that theta is the angular distance, meaning the distance or the angle within which your Ferris wheel rotated from its original position. So its original position is here, and it rotated to a certain acute angle theta. Okay, and that from that certain acute angle, we could draw its radius, and we know that radius is constant. So this is the radius, right? And from there we could see, or we could compute for the position of the ride here, or the seat here, with respect to the ground, and that's what we call height. Okay, so that's our height from the ground, and this is your y. The height is y. Okay, so in essence, if we are going to graph the circular motion, and circular motion is graphable, it could be graphed using a periodic function. Okay, a circular motion is graphable. It could be graphed using a circular function, and we call that circular function or circular motion as sinusoidal. Okay, this is also sinusoidal. Okay, or harmonic sometimes. Okay, so in this case, let us see through this graph. Well, you could see a graph here, and let's see how the angle varies, and at the same time the position of your seat with respect to the ground varies. So let us say your angle is theta. Okay, this is your angle, and this is the angle from the original position. Let's say your original position is within 11 meters from the ground. So your seat is 11 meters from the ground. So your seat is here initially. Okay, that's your initial position. Now as it rotates to theta, let's say it rotates to this. Okay, this is 180 degrees already. So look, if you rotated to 180 degrees from this position, notice that you land up in the same position, which is 11 meters from the ground. But take note, if you rotate, or if your seat rotated to 180 degrees, now presuming this is your seat and you rotate to 180 degrees, so that would be around here. This is 180 degrees. Am I correct? So at 180 degrees, notice that you still have the same height from this position here. Am I correct? So from there, your seat is at 100 or at 11 meter from the ground also. Right? So that's your position at 180 degrees. Now take a look when your position is at 360 degrees. At 360 degrees, you are landing up to the same height again, but this time it would be your original seat. Okay, the original position. So when this rotates to another 180 degrees, so that would be 360 degrees all in all. You have 180 degrees on top, you have 180 degrees below, so that makes it 360 degrees or a complete circle. Okay? So therefore, a 360 degrees is one revolution of a circle. And that is what you accomplish by doing two 180 degrees rotation. So from your original position, from this position, now you came back to your original position. Okay? So after another 180 degrees, you came back to your original position. So look at that. That is what we call one period. Okay? So this is what we call a period. You understand? So coming back to your original position is called one period. Now, how many periods do you have here? In this given graph, you have another period here, and then you have another period here. So there are three periods available for this graph. You have this, you have this. So you have three periods available. Actually, if we are going to sum it up, it would be like here, and then another one would be here to here, and then the last one would be from there to there. So this is three periods. Okay? And these are given by, the sinusoidal movement. Okay? So what do we mean when we say theta, or when we speak about theta? Theta is a Greek letter. Okay? It's a Greek letter. And this is pronounced as theta. Okay? Theta. Theta is an acute angle. So this is an angle that rotates, or an angle that carries the rotation from one position to another. In this case, this is our theta. Okay? This theta could be here. So your theta is not restricted. It could go from very low. Theta could be here, okay, as long as it comes from the center, or could be here, okay, or could be here. I'm sorry. Could be here as long as it came from the center, or could be here, and so on and so forth. So notice that your theta will vary from time to time. Okay? So what are we trying to prove here is that a Ferris wheel, in summary, a Ferris wheel is also a symbol for a circle. Right, so it's circular. Definitely it should be circular. With a certain point in the middle, which is called the center. Okay, this is the center of the circle. So we call it the center. And if we are going to draw the radius, this is the radius. And the radius is constant. It won't change from any locus in the circle. A locus is the set of points of the circle. So this circle is actually composed of millions of points or infinite points. Okay, there. So that's what we call a locus of points. Locus. Okay, so a radius to a locus there would be constant. The length of the radius is constant. Therefore, the theta varies from any angle it wants. It could be greater than 90, less than 90, greater than 180, but not greater than no, it could also be greater than 360 as long as it finished its complete revolution. So this is 360. This is one complete circle or one complete revolution. When it rotates again, it would actually could do two complete revolutions, so that's 720, and so on and so forth. There is no limit for theta along the path of the circular motion or the sinusoidal motion. Okay, so that is all about periodic functions.